This is CERN. Why am I here? Let's find out. CERN, here they smash particles together to better understand the universe. Wow. So since I'm 9, I'm not allowed to go underground, but I am allowed to ask some questions.
Hi, this is Michele. Underground here, we smash protons together at very, very high energy, at the speed of light almost. And then we study what happens when they smash. So we study what are the particles that are created, what are their properties. And this is a way for us to study nature, to study the universe.
How do the particles,
smash together? So we have this ring, and within the ring, we have two small rings where we have the protons, and they follow to opposite direction. And then we have interaction points. So this particle cross together and smashed. And then where they smash, we built around the experiment. And so the experiment in particular, this CMS, is like an onion. So you can see many different layers, and then we can understand and study what are the particles that comes out of the smash. And they are accelerated through the Large Hadron Collider with electric field. But then it's not enough. You need the magnetic field because you have to bend the particles to follow the circle, and also you have to squash the beam. So the magnets are fundamental in this architecture.
So could quantum computers help with gathering data from this?
That's the role that we have as a Quantum Technology Initiative, is to understand if quantum computer can help to improve our computing power that we have here at CERN. And since we are studying quantum field theory, we want to understand if quantum technologies are the right tool to study the nature and to solve one of the problems that we are starting to have with this amount of data that we produce and with this complex phenomena that we have to study.
You're searching for new particles, right? Like, for example, Higgs, it's called.
So we already found the Higgs, but we want to understand if this is the right one, and we want to characterize its property very, very well. So let's say that we want to weight the Higgs boson with a tool that is very, very, very precise. And to do that, we need a lot of data, and we need a lot of techniques to understand if the properties are correct. And do you know that we are the biggest producer of data in the world with respect to anything else that you can imagine? We are producing an amount of data with no precedent before, so that we have to store the data, analyze the data. So it's a very, very challenging task.
Then the quantum computers could help with that.
Yeah, exactly. So for example, we can exploit quantum computer for sampling in very efficient way the data that we have, because new particles are hidden in very, very low statistics. So we have to produce a lot of data, we have to analyze them, and we have to simulate all of this complex experiment that you see here. But to simulate that, we need to simulate quantum physics. And so we want to understand if quantum computer can do it better.
As I said, can't go down, but you can go down.
Yes.
So it's that way.
Thank you. See you later.
Bye. Bye.
We are deep underground, nearly 100 meters fact, and this is CMS, one of CERN's 4 mega experiments. Researchers here create some of the most complex data on Earth.
Standing here next to this amazing machine is so cool. Could you explain what exactly they're actually studying here?
So essentially with this experiment, you can try to study many different aspects of standard model, beyond standard model, so many kind of interaction. So they are kind to understand everything that we can extract from the collision of protons, from the understanding of the decay ratio of some particles, to understanding of the possibility of measuring rare particles decay. And of course, our reference point is the standard model. But of course, we need to test with very, very high precision if the standard model is the exact definition of what we have. So the goal of this experiment is really to go beyond what we have today and to test with a lot of precision what we can actually describe from the physics.
When the particles are going around, so it's a circular collider, right? And these experiments, if you could explain like how we capture what happens at each experiment actually.
Yeah, we have this Large Hadron Collider that is 27 kilometers. And then we have, when we have the experiment, we call this interaction point. So the two beams are across, and then we have every 25 nanoseconds the probability of smashing those particles. So we have a lot of interaction that is happening. And our goal with this experiment and also with the simulation to understand what happens is to understand which kind of particle we can create or what are their properties. 100 meters underground, we have the possibility to understand the nature in this way. So you have different points at CERN, 4, and CMS is one of these interaction points.
So what part of CMS is actually the hardest to simulate?
Essentially, you see the complexity of this detector, the granularity, and this onion structure. All of the elements need to be simulated in order to have the possibility to understand what to expect from the real data that we can collect. So everything is really complicated in terms of numbers, so millions of channels, for example, in the detector, but also the physics itself that is inside the detector. So when we take data and we smash the particle, the physics inside is very much complicated. It's coming from quantum field theory, but we are using a classical computer. So you have to understand how to approximate all of the evolution of the physics within this complex detector. And almost more than 30 meters, but then we need a precision up to micrometers. This is one of the reasons why simulation are fundamental and one of the most challenging topic also for the near future.
It's difficult to simulate because we are doing it with classical computers, is that right?
Exactly.
And nature is not classical.
That's a well-known citation from Richard Feynman, but it's actually true. And actually we can do amazing things with classical computers. But of course, if you want to go into more details, if you want to understand better what is happening inside the detector, and if you want to understand the physics without approximation, we need, let's say, a machine that should be able to speak the same language as the nature. In this case, we're talking about quantum field theory. And our role here at CERN is to understand whether technologies like quantum technologies, in particular quantum computing, could be the right solution to better understand the physics behind this huge machine.
And at which point do classical simulations actually start getting stuff wrong?
Yeah. It's always a matter of the level of approximation that we want to understand. For example, for combinatorial things like understanding of multiple interaction, you have, of course, a scalability problem, because when you increase the number of particles, and we have an effect that is called pile-up, so you have more particles that are creating in the interaction point, you need to have a lot of computational power. But also because we are trying to model something that is based on quantum field theory, we know very well that the approximation that we do with our Monte Carlo, that are very good techniques, but classic, are starting to deviate from the truth with some kind of energy. We can define different figure of merit. So again, our role is to understand whether quantum computing can be used as a model, as a technology to, let's say, compensate this kind of approximation that we have with classical computation.
So what kind of quantum algorithms actually interest physicists like you here?
Yeah, so basically here we have two kinds of problems. The first problem in the technology is just at the hardware level. Because of the rate of the collision is very high, it's 40 megahertz. Then there is a cut that you have to apply, a filter that is really hardware based. So at this level, we are not entering into the game, because it's really kind of hardware development that is needed to collect all possible data that we are generating. But once the data are collected, so actually we can store them in some kind of storage, let's say classical storage, then the idea is to understand if with quantum algorithm we can improve, for example, classification. And this is specific for data analysis. But I would say a complementary part of what we can study here are simulation. So we need to simulate very well what is happening, because in the end, the way we do research is to compare the data that we can collect from the experiment and what we simulate according to the model. And of course, the two things should match. So our idea is to use quantum computing and quantum algorithms, for example, to develop quantum generative models. So models that are able to sample the complicated, I would say, probability distribution that characterize those particles in a more efficient way. Of course, there are a lot of things to be done, but there is some potential. And of course, our goal is to understand how to help the community for the next year, because with the new upgrade that is coming, we are going for sure to suffer from a computational power in terms of GPU, in terms of capacities to store this information, to analyze this information. So there are different directions where quantum computing and quantum algorithms can help.
So Could we see where all this data is getting analyzed?
Yes, for sure. We are going to see where all of this data that are collected here from the experiment are analyzed for the first time in the control room, so we can go together.
Great.
These are all normal computers, not quantum computers.
Actually, a lot of the things that you see here and all the cameras and all the programs are done with classical computer. They work very well, but we know what are their limitations. So our role here is to understand whether a quantum computer can be helpful.
Can we see the collisions with the particles that go?
Yeah, exactly. One of the things you can do from here as a control room is to understand that the electronics that is collecting all this collision is working fine. So you will have a representation of different parts of the detectors that are lighting on. That means that particles are hitting in different places, and then someone will need to understand who they are and what are their properties.
And so would quantum computers be better in finding some really cool rare events as well?
Well, in general, we try to understand whether a quantum computer with quantum algorithm can help supporting what we are doing with classical one. For example, looking for rare events, we know sampling properties of quantum computer, and so we want to understand if a quantum algorithm can be used together with the current infrastructure, if we can use quantum computer for simulating what we see here to understand if the data are collecting are aligned with our theory. So there are different directions, and of course, the goal will be to make quantum computer work together with the classical and the standard infrastructure that we have now. Quantum computer can be used for what we call offline analysis and offline simulation. So there will be a dedicated space where quantum computer will prepare the data for us, and then we will compare the data we collect in real time. So at the moment, I don't see quantum computer for real time, but as a tool to be used to support the analysis after we collect all of the data.
And the data right now is kept in the data center here at CERN.
Yeah, exactly. So we have this beautiful architecture called worldwide LHC computing grid. And essentially what we do is that we collect the data here at CERN, and then since the data we have a lot of data and a lot of analysis to perform. Then after the collection, they are distributed to different data centers that are called tiers, so tier 0, tier 1, so on and so forth, all over the world. So that's a very fancy architecture, and we want to understand if also quantum computer can be part of this distribution.
Okay.
So I heard magnets being used here.
So we have 27 kilometers of magnet distributed all over the LHC. So essentially their role is very important because after we accelerate a particle, as we discussed, it's important to bend them because they have to follow the circle. And also when we bend the particle, we can understand their properties because of their trajectory. So the magnets are fundamental to create this deviation to the particles and also to squish the beam, because we want to have more particle condensed together because we want to increase the probability of meshing, because it's very small, but it's very empty. So we need to make the particles very, very close together. And this is done together with different kind of magnet.
Okay. Can we see the place?
Of course, we can have a look together. Yeah.
Great.
Where are we now?
SM18 is the place where we test and produce the magnets that are part of the Large Hadron Collider. A magnet is composed of many elements, and each of these elements have a different role, but essentially we bend them and squeeze the particle within the accelerator.
What about the upgrades of the LHC?
Actually, it's one of the biggest upgrades that we are going to have. So basically what we want to do is that we want to increase the amount of particles, so the density of this interaction. And the only way we can do it is by increasing the amount of magnetic field. So we need to move from what is around 8 Tesla now up to 12. And this is a major upgrade. And to do that, we have to work a lot on the materials that are creating this magnetic field. So there is superconductivity here, a lot of common points with cryogenics for quantum computing.
So could quantum computers help with this upgraded LHC with magnets?
Yeah, well, with magnets, let's say that we can try to understand if the technology that we use for the upgrade of the magnet is something that can be reused for quantum technologies in general. So to improve our understanding of superconductivity or the cryogenics that we use for quantum computer. And also, let's say that with the new upgrade, we have a new challenges for the computing paradigm because we will have a lot of more data. And so quantum computer will play, I would say, I hope so, a fundamental role in helping us analyzing this data and improve our simulation for this very dense collection of particle data.
Great. Well, thank you so much, Michele. Thank you for your time.
Thank you.
Thank you for coming.
Thank you, and have a great
Ciao.
day.
See you. Bye.
Bye.
Bye-bye.
And thank you, of course, to our viewers. Thank you for joining us, and we'll see you next time on the Quantum Kit.
And by viewers, we mean you to now click that like and that subscribe button.
Thank you, and goodbye.
Bye.